Hey, hello friends, and welcome to another video of this series. In this video series, we are making a IoT hardware from scratch. And since I wanted to make this series beginner friendly, so we are talking about the core concepts of passive components or the common electronic components and their hardware design application. In the last couple of videos, we talked about capacitor, where we went through the types of the capacitor. We talked about application circuits. In this video, we are talking about resistors. We'll go what are the types of resistors, and then we'll see the applications like current limiting, voltage divider, pull up and pull down, power dissipation, sensing and measurement. Before going ahead with the video, I would like to thank Altium for sponsoring this video series. So Altium is one of the best PCB designing software, and Altium offers Altium 365, which gives you a flexibility to design a, a electronic product from scratch to the production, where multiple stakeholders can work together on that project, be it the requirement, be it the schematic, be it the BOM management, be it the board design or the QC testing. Everybody will be able to work on the same platform seamlessly. If you want to learn more about it, you can go and watch this video. I have a link in the description. You can go and check that. So, resistors are essential passive components in embedded hardware design. They limit current, set voltage levels, and can be used in variety of ways to influence the behavior of electronic circuit. Now, these are the different types of resistors. The most common which we used on the PCBs are the SMT ones. Okay, there can be few applications where you need a through hole resistors, and these are of like carbon composition or can be of carbon film resistors. When it comes to these resistors, wire wound resistors, right? So these are basically used for making DC load or used as a dissipation of energy, and NTCs, right? So these are negative temperature coefficient. So these are used for a sort of a temperature sensing. Okay, then you have potentiometers over here. Okay, so let's go ahead with the applications of these resistors. So when it comes to fixed resistors, it has a set resistance value and doesn't change. And the applications are like voltage divider, current limiting, pull up, pull down, biasing. When it comes to variable resistors, when we talk about potentiometer, right? So they are used for volume controls. So in case you are having any sort of a audio device or a FM radio, you basically rotate that knob. Based on rotating that knob, the resistance changes, and based on that, different channels from that radio are set. Then you have rheostats, which basically is used to control the current flowing. Okay, so the most common one which is for the PCBs are the surface mount resistors, and these are used. So these are, again, the application remains the same, but if I talk about what else, so it is used for space saving design, ideal for compact design, often used in modern electronics, and it is used for high frequency circuits. Then you have specialized resistors like thermistor, as I talked, NTCs, right? So negative temperature coefficient, positive temperature coefficients. So these are used for temperature sensors. Okay, and then you have LDRs. So LDR are light dependent resistors. Yep. So wire wound resistors are used for high power circuit and the precision application. Then you have power resistors, and these are used for current limiting in high power systems. So let's see the application of current limiting. So if you see, right, this all schematic snapshot I took from the open source schematic from Adafruit and SparkFun. Okay, so if you see, there is a LED D1. Okay, and it's been connected to the power source, and you have 4.7 kilo ohm resistor connected. Okay, so why this resistor is there, right? The resistor is there so that it can limit the current flowing through the LED. Okay, so we'll see this in detail. Okay, let's say lipo charger, right? So this lipo charger also have a LED over here, and if you see in this series, you have 1k resistor. So the difference is, here you have a 4.7 kilo ohm resistor, here you have 1k resistor. Here the input supply voltage is 5 volt because it is coming from USB. Here it is 3.3 volts, and here is again, it's from a digital pin 13 of some MCU, where you have 1k being connected. And this shows it is a blue color, this shows it is yellow, this might be red. So if you see, right, these LEDs are there. Okay, and then you have a varying resistors. And the reason for using this resistor is for limiting the current flowing through this LED. Now let's talk about how these resistors are getting selected. If you have to design something like this, and let's say I replace this yellow LED with a red LED, so will my resistor value will change? Obviously yes. Now to change these LEDs, or to change anything in terms of resistor, you have to first see what is the spec of that LED, what is the electrical characteristics of that LED. So let's see. So you can come to this website, I'll link this. So this is a calculator from DigiKey. And if you come down, right, based on LED colors, you have typically the forward voltage range. Okay, so this is what the resistance formula is. So it talks about the voltage at the source minus the forward voltage of the LED divided by the forward current of that LED. So in this circuit, I will be common, right? The current going through this LED will be the same as what it goes through this resistance. Okay, so let's say for an example, let's come back to the design. Okay, so this is what the hardware, where we have to see why this is 1K. So here there is no part number mentioned, right? So we'll just go by some assumption. So this is a yellow LED, right? So the typical forward voltage ranges from 1.9 and it goes till 2.2. Okay, so for the simplicity, let's have this as a 2. Okay, or I can even change it to, let's say, 2.1. Okay, now since the bus voltage, right, the supply voltage here, if you see, it is coming from the USB. So maximum it can be around 5 point something, but let's take 5. Okay, and the forward current would be somewhere around it ranges, it differs for LED to LED. It can be even 10 milliamps. Okay, if we do 10 milliamps, right, you see the resistor value needs to be 290. But if you adjust this to 3 milliamps, right, we are getting some 966.667. And if I change this forward voltage to 2, you can see we are getting 1000. That means 1000 ohm, 1 kilo ohm. And if you see the schematic, it talks about, okay, there is 1 kilo ohm and there is a yellow LED here. So that LED, right, now we can search for this part, a LED that has a forward voltage of 2 volts and a forward current of 3 milliamps. Now let's see, like, in detail how this calculation happens, right? So here is a typical example that has been given. So it's a 9 volt battery being connected. You have a LED, okay, where you have the forward current, the forward current to be 20 milliamps. And then you have to calculate what would be the resistor value. So you can go through all this literature. At the end, it's the same thing. Okay, now the only critical thing which you meant see here, right? When you select a resistor for this purpose, choose a device with a power rating between 2 and 10 times the value calculated. Below is the order to avoid the excessive resistive temperature. So uh, let's say for this resistor, right? So calculated value is uh, 1 kilo ohm. Okay. Now if you have to calculate the power, okay, so the power is I square R, right? So in that case, if I come to this calculator and I'll say, okay, my resistance value is this, and the current, whatever would be, like, let's say 3 milliamps. Okay, so I'll go to milliamps. I selected 3 milliamps, and the voltage. Okay, so since this is 5 volts, okay, and there is a forward voltage of 2 volts. Okay, so this v1 v2 is equals to the v, that means this is 2 volts. So this becomes 5 minus 2, 3 volts. So let's have this 3 as well. And if we calculate, this is in watt, let me convert this to milliwatt. So if we calculate, this becomes 9 watt, right? That means whatever we have to select the power rating for that resistor, it should be twice or and 10 times. Okay, it should be between this. That means you can go for a resistor having 90 watt or 18 watt. So double of 9 is 18, or 10 times is 90. but usually you will have 1 by 8, 1 by 12th watt of that resistor value. So this is how you can calculate what would be the resistance value when you select the LED. Now let's search some LED. Okay, so this is again a single color red LED. Okay, so whatever in the schematic we saw, it was a yellow LED, but we were going to use a red LED. If you see, right, the forward current is 20 milliamps, and the forward voltage is 2 volts. The power rating is 75 milliwatt. Okay, so this is what for the LED is. Now if I go back to the calculator, where I say this needs to be 20 millivolts, okay, sorry, 20 milliamps, and the forward voltage is 2 volts, okay, and the supply is 5. If I see, right, now the value becomes 150. That means you can have a 150 ohm resistors being placed instead of 1k. So if in this circuit I'm going to replace this, I can replace this with that part number, and I can use that resistor. In terms of rating, since uh, this it's 150 ohm, right, then I can come to this power calculator, put this 150 ohm, okay, and the current was 20, which will be common for resistor as well, and the voltage drop across the resistor would be 3 volts. So if I click on calculate, this becomes 60 watt, right? So I have to take something double this, so 180 watt milliwatt would be the correct power of that resistor. Okay, and this resistor is basically limiting the flow of current. So let's say if you use a higher rated resistor, right, what it will do, right, it will dim the LED. Your intensity or lumens of that LED will reduce. And if you are using a lower rating resistor, it will spoil this LED. Okay, so this was all about current limiting. Let's go ahead with so whenever you are having any generic LED indicator or any LEDs, it can be a SMD of a package size of 08051206. You can go ahead with 1 by 8 watt rated resistor. When you are using, for let's say you are using a very small size LED, then you can go for 1 by 16th watt, and this is basically for low power circuits and signal path. So this was a small cheat sheet which you can use to select the resistor power rating, and this is the typical common use case. Now coming to another application of this resistor is current regulator. If you see, we have a LDO. So this basically, you have, let's say you have 5 volts, right? You can, the V out can be 3.3. In case you want 3.7 or things like that, you can have a fixed output, or you can have a adjustable output. So whatever here you have, right, here we are adjusting the current. So if you see the I out formula, the current that can flow from here is V reference, which is basically for this LM315. If you go through the data sheet, it is 1.25 volts, and then you have R1. So R1 is here, and then you have I adjustable, right? So this is basically a sort of a feedback, and this is very less. It's somewhere around in micro ohms and all. So we can ignore this. The moment you ignore this, I out is 1.25 volt by R1. Okay, and now this LM315 can give a output current from 10 milliamps, and it goes till 1.5 amps. So with change in R1, okay, you can control the I out. So if you say R1 becomes 1.25 volt by I out, so if you have to take, let's say, 10 milliamps current, then you can use a 125 ohm resistor. If in case you want let's say 100 milliamp, you can use a 12.5 ohm resistor in place of R1. And in case you want 500 milliamps, you can use 2.5 ohm. Now um, in terms of rating the value, we will be able to select based on whatever the current we need. But in terms of, let's say, the power, now power equals to V square by R, right? So this becomes 1.25 volt into I out. Now I out is basically based on, let's say if it is 50, okay, so it becomes 1.25 volt into 50. And for 1 amp, let's say as a simplicity, it becomes multiplied by 1. So P equals to 1.25. Okay, so anything above 1.25, it's better to go with a 2-watt resistor. If in case you want 500 milliamps output, so the power becomes 0.625. Here you can use 1 watt resistor. So this is all about how you can use a resistor to control the output current. So if we come to the example schematic, right? So this is a battery charger circuit that uses MCP 78831. And here if you see, you have R program, which is this R10 LED. Okay, so if you are putting 4.7k, the charging current is 213 milliamps. Okay, so whenever you use a battery, the battery will have a C rating. Based on that C rating, you will decide how much of current that battery can take. Based on that current taking capability, you have to change this resistor. Let's see some other example. Okay, so this is one of the example where you have basically the values of the resistors, and based on that value, how the VBAT current changes. So if you are using 10k at this place, let me zoom in there. Okay, so in case you are using 10k, you have 100 milliamps. If you are using 5k, it's 200 milliamps. So if in case you change this resistor value, the VBAT value changes. Okay, the current going to the battery will change. So let's see this. Okay, let me search this part. So this is MCP. So this is the part. Let's go to the data sheet. So this is the data sheet of the part, and this is the typical application circuit. Let's come down. Let's zoom it here. Okay, so if you see here, right, you have the charging current I out versus the programming resistor, which is the R prog. Now if we come to the schematic here, right, so for 5k, the charging current would be 200 milliamps, right? So let's see that here. So the 5, so this is the resistance, right? So the 5k will lie here, and if we go up, right, this is where the 200 is. Now let's say if in case you want some, let's say 25 milliamps charging current, right, so that will lie somewhere around here. So that needs, you need a 37 kilo ohm resistor. Similarly, based on this curve, you can select what would be the resistance value, and corresponding to that, what would be the current. Okay, so let's go ahead with our presentation. Now we'll talk about voltage divider circuit. Okay, so this is the final part which we are going to use in our upcoming hardware design. So this is MP2338, and it takes an input of 28 volts, and it can have a continuous current output of 3 amps. If you see here, right, we have this feedback pin. We'll come to the detail of this step down converter, okay, in upcoming videos, but we'll just focus in terms of how this 5 volt 3 amp is there, and how I can control the voltage output, right? So this basically is a voltage divider circuit over here. Now here you can see this F6 have RT, R1 and R2. Okay, and then you have a feedback capacitor. This 300 picofarad is a feedback capacitor, and then we have RT we can take as R6 over here, and then we have R1 and R2 as a value. If you see the table over here, okay, so first of all, let's see the R1 value. So R1 equals to V out minus Vref by Vref into 2, okay, into R2. So here is a quick table where you can have a comparison done. Okay, so ideally the Vref is around if I'm not wrong, it is around 1.2 volts. Okay, if you put that over here, and in case you want, let's say 1.8 volts, you can put the RT value as 16.9. You'll be able to get the R1 value as 51. So if you see in this chart, right, you have R1 and RT fixed, and we are calculating R2. So Basically R6 is 10k. Okay, R2 also you can fix to 10k, and then you can calculate what would be the value for this. Now based on based on this value, if you see from 1 to 3.3, the only value which is changing is R2, right? Your R1 and RT are constant. So based on changing the R2 value, you are able to get a different output. Okay, you don't need to see capacitor and inductor for now. This we will discuss in detail in upcoming videos. So here you have a voltage divider circuit. Okay, based on that voltage divider circuit, if you change these combinations, you'll be able to change the output voltage here. Now let's see the concepts like pull up and pull down resistors. So in any hardware, microcontroller and all, you would have seen there are few pins which are floating, then there are few pins which we pull up or pull down. So pull up and pull down resistors are used to ensure a defined logic on an input pin of a microcontroller or other device or digital device when no active signal is present. So as a definition, if you see pull up resistors, right? So a pull up resistor connects to a digital input pin to the positive supply, and this can be 3.3 volt or a 5 volt. When the input is not actively driven low, the pull up resistor ensures the input is pulled to a high logic level 1. So application is basically to prevent floating inputs. Sometimes what happens if you have left pins floating, right? Then it can show some random behavior the moment there is any signal changes. Okay, so it's better whenever specified in the documentation or the spec sheet of that microcontroller, or that part, right? To do a pull up and pull down, you should, if it is pull up, it's better you connect a resistor and provide 3.3 vcc or 5 volt to that. So basically, it prevents, without a pull-up resistor, right, unconnected or a floating input pin could randomly pick up noise, causing unpredictable behavior. And used in switches, we'll be seeing this application. So when a switch is pressed, it can pull the input to the ground. When the switch is open, the pull-up resistor ensures that the input is at a high signal. I2C communication. So in you will see like SDA SCL lines in I2C communication often uses pull-up resistor to ensure proper high level voltage when the bus is idle. So this we'll be seeing in examples where we will be using SD cards. And similarly, pull down resistors, basically you ensure that pin is being pulled to ground. Okay, again it prevents a similar thing the way the pull up resistor used to do, and they are also used in switches as well. And for the logic gates, to use for certain input logic gates to a defined state. So let's see some example. Okay, so if you see here in most of the examples, you will see this is a pin from ESP enable. Okay, and this, if you see, there is the reset, there is a button, and once you press, then only this connects, right? And this gives a low impedance path. But when it is open state, right, this pin is being plugged to 3.3. Now why there is 100k resistor? The 100k resistor basically ensures there is a very minimal amount of current floating. Okay, so if you calculate the current floating, right, you need to have you can go through the data sheet. The data sheet will tell you ki at that ESP enable pin what would be the expected current. Okay, and based on that you can select this, whether it is will going to be 100k or a 10k. Now let's see the other one application, right? So whenever you are pressing this button, right, what happens? The moment you press this button, it gives a low impedance path. Okay, and the ESP is now pulled down. Okay, and whenever it is there, the reset button is not pressed, this will be pulled up. Same goes for the boot pin application, where you will see the moment you press this. So currently I boot, let me show you the full schematic so that you can understand this better. Okay, so this is basically to enter bootloader, hold the boot button when ESP32 resets or power on. So this is basically, you can press, the moment you press, the ESP will get reset. The moment you press, okay, and hold this, it will get into a boot state. So if you see, this boot pin is connected to ESP32 MCU or the module. So here we have to see where is the boot pin, right? So the boot pin is IO9. Okay, and this has been floating in the sense, until unless you press this, okay, it won't be grounded. Okay, you have a debouncing capacitor over here. Now let's go to some other circuit. So this is from ST microcontroller STM32F405. Here if we see, you have the boot pin and a switch. The moment you press the switch, okay, this will get pulled up. Okay, so if you see here, already, right, as a default this boot 0 pin is pulled down. That means there is a resistor connected and it's been grounded. Now the moment you press this, right, the moment you press this and there is no resistor on this path, so based on the low impedance path, right, this becomes a low impedance path, and the pin will, and the boot 0 pin will basically get pulled up. So this is how the application is there when it comes to pull up and pull down. Similarly, you can see the reset also being the same way. Okay, the way it was used in ESP32. So here you have a pull up being done for 4.7 kilo ohm, and the moment you press this switch it gets pulled down, and you have zero point 0.1 for debouncing. Okay, so whenever you press, always it's good to have a capacitor in parallel to the tactic switch. And the reason this is 4.7, and the other board which we saw, right, here it was 100k. Now these values is defined based on the enable pin and the current it can sync. Okay, so when you go through the data sheet you'll be able to understand, we'll be seeing all this in our schematic capturing video of this series. So let's go back to the presentation again. So we talked about this, okay, and here you can see, right, a pull-up resistor that connects the reset pin to 3.3 whenever you press, and you have this zero point 0.1 as a decoupling capacitor to use to filter noise and stabilize the voltage when the reset button is pressed. Similarly, the boot pin is there. Now, one interesting fact which you will see when you go through the data sheet is basically based on the state of the boot pin. Okay, based on the state of this boot pin, you can put the basically either the MCU can get into a download boot mode, or it can run through the default configuration when it is floating. So this was all about this video. We learned the concepts like current limiting, current adjustment, pull up, pull down. So these are the core elements, or I can say the core application of resistors that we'll be using in this video series. I hope you guys like this video. Thanks for watching. If you have any question, you can comment. See you in the next video.